So, hello everybody, and hopefully you enjoyed lunch. My name is Scott Murray, and I'm going to present on Vehicle Signal Specification and Cooksa.val in automotive grade Linux. Just a little bit about myself. I've been a Linux user and a developer pretty much since 1994. Did some scratch my itch type of Linux device driver stuff in the early days. I've been an embedded Linux developer since the year 2000. And since 2014, I've been a principal software engineer at Konsulko Group, which is an embedded Linux consulting company. I've been working on AGL on contract since 2016. Pretty much full-time since then. There's been a couple of brief periods where I was a little less than full-time. But pretty much I've been helping out with the Octo project maintenance since the beginning. It's sort of for a long time, it's been my sort of area of expertise. But I am sort of a systems generalist, so I have done a bunch of demo development and integration of various pieces of AGL development, like the app framework, and general maintenance and helping Jan Simone with various things. Here's my agenda for today. I'm going to talk about vehicle signaling services in AGL pre-Marlin release, and then I'll go into what the vehicle signal specification is, as well as vehicle information service server. I got it backward on this slide. And then what Cooksa.val actually is, and then I'll talk about how we're using VSS in AGL today, and then I'll finish up with some future development discussion. So if you've been around AGL for several years, some of this won't be news to you, but pre the Marlin release, so 13.0, we were using the application framework, what we call the legacy application framework at that point, these days. In that, the vehicle signaling, we used two API bindings, the AGL service CAN level and the signal composer. So those were developed by the folks at IoT.BZH for AGL, and we used them in the demo platform to implement the dashboard, the instrument cluster dashboard, HVAC support, and our steering wheel demo was all wired up with those. I'll sort of elaborate a little bit on them. So the CAN level was based off of signal definitions for using OpenXC, which is a Ford project that they sort of threw over the wall. I think it's still probably on GitHub if you dig around enough. And it had basically an XML schema to define CAN signals. And the issue we kind of had there is AGL was probably the only project using it that I could ever find. And so there was no user community around it. And the code generator basically, to take the XML and generate code for the app framework binding, we used some libraries that came out of OpenXC. So we were sort of the de facto maintainers of some of that stuff a little bit, but it was all inside our application framework binding code. So it had a sort of easy to understand API for subscribing to signal updates, writing, getting, that type of stuff. And the IoT.BZH folks had some J1939 and ISOTP signal support. But when that landed was right around the time that we were starting to think about when maybe the application framework is a little too big and something that isn't really of a lot of interest to the members. So we never really fully exercised some of that support in AGL. And the ISOTP we never actually turned on. I know the IoT.BZH folks were using it, I think, in some of their demos, but we never actually used it. So the signal composer, which is actually a little more relevant to this discussion. So the signal composer is a service that abstracted signals from multiple sources. So basically, the CAN binding exposed things that had very much CAN naming, typical CAN signal naming, coming out of that OpenXC XML definition. And Signal Composer, you could abstract that to have a more generic namespace. And in the demo setups, that's what I did. I had more abstract naming for signals for apps to see. It used JSON configuration, and it had some runtime loading of the configuration sort of possibilities. But one of the big knocks on the Signal Composer is that its plugin architecture and the way the signal processing inside was all very much based on the guts of the application framework. So when we were talking about, well, let's drop the application framework to kind of cut how much code AGL carries, it kind of made things like the KNLO level and the Signal Composer difficult, because it was like going to be a lot of work to reuse some of that code. And like the KNLO level, we were using things that basically there was no community. So specifically for the KNLO level, we had a couple of workshops and calls where the question was put out to the AGL membership: do you want AGL to actually build some low-level CAN sort of system, API or daemon? And sort of the answer was no, because most AGL members already have a CAN framework that they've either built in-house or got from a tier 1 or purchased from a tier 2. And there is no real open source project that you can point at and say, here's an open source project with a big community that actually has a comprehensive CAN system. And the only thing that really is in that space is the Linux kernel socket CAN support. So sort of our mode of operation right now for CAN is we will leverage things that sit on top of socket CAN and not try to build anything elaborate ourselves. So that's that part of the system. But then on the Signal Composer side, to have something more useful for applications, while we were working on taking out the app framework, I found in 2021 that there was this sort of project started, the Vehicle Signal Specification and Vehicle Information Server standards, were things that had come out of KUKSA. And that sort of looked, after some investigation, that a VIS server would probably give us something that looked like Signal Composer, but wasn't something that we in AGL had built. We could actually join that community and leverage an existing project and contribute to it. So what is the Vehicle Signal Specification? I'll use VSS as I go along, just to kind of shorten things up. Like I said, it started under KUKSA, formerly Geneva. It is a major component of the KUKSA and W3C Common Vehicle Interface Initiative, CVII, which is an ongoing thing where they're starting to leverage technologies for software-defined vehicles and things like that. So the specification was developed by BMW, Volvo, Bosch, Jaguar Land Rover, and some other smaller tier 2 companies in the geoinformatics type of space. So there is an ongoing standardization effort with the W3C. I'm not including the link here, but if you poke around, you can find actual revised, B1, B2 standards sort of drafts. So what is it actually? So it is a hierarchical signal schema, and if you attended Sten's talk yesterday, you'll have gotten some of this as well in more detail. But so basically, there's a tree of signals. And each node in the tree, like a leaf, is actually a description of a signal. So like a signal name, typically we use the dotted formation here. So you'll see this vehicle is the highest level node, and then you work down. So the RPM value for your engine is typically this powertrain combustion engine speed value. And typically, at least what we consume, the schema is a big JSON file. But that's actually generated from higher level metadata, which it's actually a format they call VSpec, but it is a YAML input. And so there's tooling that can generate the VSS output to consume in a bunch of different formats. And that's all carried in the VSS specification repository. So currently, the schema is at 3.1. I think it came out 2 weeks ago. And one of the big recent additions is they added support after a whole bunch of debate for structured data types. So you can kind of define in the schema returning a struct for a signal value, which so far we haven't actually done anything in AGL where that's become an issue to use it, but it might at some point. So that's VSS, but on its own, that's not useful to us, right? It's just this big JSON file of signals. So you need something that actually exposes that to you in a usable way. So that's what the Vehicle Information Service Server is. It is also an open source project coming out of KUKSA, which makes sense. Like they're defining the schema, they have something to use it. Similar set of companies, of course, worked on it. It's also undergoing some standardization around the protocol to talk to a VIS server, which is a WebSocket API to access the VSS signals. So, unsurprisingly, it has get and set and subscribe API calls. There's a reference implementation in Go that's on that GitHub, on the W3C sort of hosting there. There's also a partial implementation in C++ in Cooksa.val. Some of which if you went to Sven's talk, I'm now going to be started duplicating a little bit of what Sven talked about. So Cooksa.val, this is up on GitHub. It's hosted by Eclipse these days. It's primarily developed by Bosch with contributions from some other companies as well. It implements most of the Vehicle Information Service V1 draft and some of the V2 draft changes. It also extends VIS with a gRPC API, which echoes most of the API calls. It's very similar, get and set and subscribe type of things. It has an authorization mechanism for signal access that's based on JSON Web Tokens. And as well, in their source tree, they have Python and Go client libraries that you can use in your applications. And the big thing for us when we were picking something up to be able to build a working system to demo it is there are example feeder clients to push signal data into the Cooksa.val server so that you can actually have data show up for applications to see. So that I'll get a little bit more into that as we go along. One of the other nice things that Cooksa.val has that I don't believe the reference implementation does is it has a straightforward mechanism to show new signals. So you can basically supply a chunk of JSON that overlays the VSS schema and adds some new signals, which is we use a bit for a handful of custom signals for our demo setup, which are there in that link. So what are the feeders exactly? So for CAN, we use what they call the DBC feeder in Cooksa.val. It uses CAN database file, which is the vector file format for CAN signal definitions. But it is sort of documented on the web. So like I wrote the one we're using from scratch just by reading on the web. And it pushes the selected CAN data for the signals in your DBC file to the Cooksa.val server based on a configuration file that maps CAN signals to VSS signals. As well, there's a GPS feeder that you can use to actually push location data in. It's basically just Python script that hooks up to GPSD. And there's a replay feeder that you can use to actually record a set of VSS signal updates and then play them back later for testing. So that's the technology, Cooksa.val, right? And so it is what we're using in AGL today. So how exactly are we using it? So I first added the server in Marlin, so the 13.0 release, because that was where we had taken out the app framework. And we wanted to have something in place to show, we still have vehicle signaling support. So there's a recipe to build the server, the Yocto recipe in Meta AGL demo. As well, there's some stuff in there to install our custom signals, the JSON file that I had the link to, and to build and install the DBC feeder because we need that to be able to actually push data in to actually use it. And so our DBC file is, like I said, I wrote one up. It's based on what we were using with the old CAN binding. There's an AGL virtual car, sort of minimal set of CAN signals. which could stand to be updated to have a lot more added to it. It's very minimal. Basically has vehicle and engine speed and a handful of other values. So that's our server, right? It's built into most of the images these days, and we have our configuration for it and for the feeder. So how do we actually use this? In the application side, there's sort of two categories that are sort of, you can pick out of what we've done. So there's pure observers, basically, of VSS signals. And so those are like dashboard applications. And in VSS terminology, there's sensors and actuators. So the observers are basically subscribing to the C sensor updates. So vehicle speed type of things. As well, there's things that I'm referring to here as actors that basically, when they see a signal update, do something. And that is what an actuator is in VSS. So an example in AGL is our AGL service HVAC. So I'll expand on what AGL service HVAC does these days. It used to be an app framework binding that used the application framework API, and it basically the Qt demo HVAC application, or sort of the dashboard, basically would receive updates from the application framework API calls and would drive out over socket CAN to the HVAC controller in the demo system. At one point, we actually did convert it to use the right support at AGL service CAN low level. But of course, we pulled out AGL service CAN low level as well. So when we removed the application framework, we still had all this code there. So I basically took it and I reworked it to use VSS signals as input, instead of using the old application framework calls. So VSS does include a very comprehensive set of HVAC control signals. There's 4 rows of left and right temperatures and fan speeds. And so you can see here, there's an example of what those look like if you were to do an update or actually potentially see a value of a change come back as a notification. These is what they look like. So AGL service HVAC basically starts up and subscribes to listen to changes to these, and then pushes out to the HVAC controller any updates. So implementation-wise, it's in AGL Garrett in Git. You can actually go and see the change set of when it would change from an app framework binding to this new service daemon. I'm currently using the WebSocket client out of Boost just for convenience sake. But Cooksa.val, like I said, has a gRPC API. Probably in the very near future, I'm going to go through and start changing things over to use that. And then, like I said, it listens to fan speed updates and pushes those out. As well, Jens Simone in the demo system has a way to actually control some LEDs to show temperature changes. So that's actually pushed out to actually GPIO with some gross looking code. So that's there. You can actually go and see how to build a simple client that actually acts as an actuator sort of driving service. So that was the first thing I think I built. The second one was the audio mixer. So when we were coming up to CES 2022, I guess, we didn't have a way to actually drive the audio volume anymore because, I guess this was Embedded World last year actually, because the audio mixer API was all app framework stuff. So it sits on top of Wire Plumber, but all the controls were app framework. And so we still wanted to be able to have volume control to show that off. And VSS has a main volume control signal. So I basically took the audio mixer code and refactored it to basically wire it up as a VSS client. And it looks for changes to the media volume, and then it pushes that out using the code for, to talk to Wire Plumber. One thing to note, though, is the VSS schema really only has this main volume control. It doesn't actually have a way to expose per roll fine-grained volumes. And so we'll probably actually still define a separate API for those this year, I'm guessing. So that's our two service things that basically drive actuators. As well in the demo applications, we have the QT demos, the sort of more traditional things that we have now, our legacy is maybe too strong a word, but they're, slowly we're working to shift to the focus to Flutter. But in the QT demo applications, the dashboard, we use the VSS vehicle and engine speed signals, as well as there's a display unit signal for like metric versus imperial, which I don't actually have a thing in the settings app to drive it, but if we do wire it up, it will actually work. I have tested it by hand before. The cluster dashboard for the QT demo also has the same support for the vehicle and engine speeds, as well as some navigation and cruise control signals. And some actually, it's wired up for some of the custom signals for the steering wheel demo. So things like some of the ADAS switches on the steering wheel demo actually go to custom signals that then kind of get sent back to the cluster demo app. There's some potential. I need to sit down and actually look at VSS 3 more carefully. They have added some signals in the last 6 months. I might be missing some things that I could switch us over to a standard signal for a few things. The home screen app actually uses the volume control, so when you adjust the volume slider in the home screen, it's basically doing a update that Cooksa.val gets, that then the subscription that the AGL service audio mixer has made, it gets a notification of your change, so you see that going in and back out. And at least in the QT demo apps, all of the WebSocket client code is in libqt app framework vehicle signals. So it's sort of abstracted, and there's a QT object that they use, all the demo apps, to actually sort of cut down on code duplication. So that does have a follow-on benefit I'll talk about in our future development. We will still maintain these apps, so there's still some potential fixes we can do in that space. For the Flutter demo apps, which you'll see if you see the current demos, very similar. The dashboard app uses the vehicle and engine speeds, of course, but it actually, the JSOC students did a really good job on some of this. They've actually wired up a lot more signals than I did for the original QT apps. So like there's tire pressure and door locks and things like that. Slight issue is right now in our demo, we don't actually have anything wired up to push data in to update those values. So effectively, when we boot up, those get initialized to a static value. But if we ever do work out a good simulator setup, we could actually start showing, these things being changed dynamically in the Flutter apps. The cluster app is similar. It actually has more things wired up in the QT. It has the turn signals are actually coming out of VSS, things like the headlight state and parking brake and stuff like that. So the home screen is, of course, still has to have volume control, so it's also done the same way. And in the Flutter apps right now, the WebSocket client code is basically duplicated in each of them, but it isn't a lot of code. Dart is pretty good about that, so there is some potential we could maybe make a module at some point, but I'm not too worried about it just yet. So that's currently what we've all put, between some of the GSOC students and myself. That's kind of where we're at. There's a little more nitty-gritty behind the scenes stuff, but that's the high-level view of how we're using VSS today and Cooksa.val. So on the future development side, some of these are proposed tasks that some of the expert groups, or at least the app framework and security expert group have proposed. And so I can't say that all of this is going to get done necessarily, but this is the plan. So on the application side, we're pretty much geared up to change all of our existing clients to use the gRPC API, which is sort of in line with the goal of demonstrating using modern IPC that AGL has sort of set a stake in the sand like in 2020 that we're going to try and shift to something more modern. Protobuf-based code is definitely more robust than JSON parsing, so it's a big win on that front. And hopefully moving to one IPC mechanism should make it easier to show how we can secure API access. And on that front, I believe if you were at At Roger's talk, he was talking about how the certificate stuff around access to Cooksa, that's one of those things where we do have the same issue if we switch to gRPC, is we have to have this authorization token and get it to the app to then pass to Cooksa and get access. So working out a good way to show AGL members, like, here's a good way to do these kinds of things, is one of the things I want to get squared away this year, hopefully. So systemd in recent versions has a credentials mechanism where systemd can securely give a started application, some files or, a chunk of memory that basically has certificates in it. So that's one option we can consider. There's also things around OAuth and some of the other public key stuff that comes out of the cloud that maybe we could look at. And to sort of, to Walt's call for, improving our documentation and developer workflow, I need to actually sit down and, probably myself and maybe Aman or somebody has to document some of this stuff in a better way for people to jump on. Likely at a high level, we want these AGL Service Network and AGL Service Bluetooth, some form of replacement for the old app framework bindings, because right now our settings app, we have, like in the Flutter demo, we're still using the Qt demo settings app. We could, potentially just write a Flutter app that talks dbus to Conman and BlueZ, but that's not that appealing really. And would make life quite difficult for like the web apps and stuff. So we'll define some form of gRPC API for those, but it does sort of come back into VSS a bit because it doesn't have detailed network configuration, but there are some signals around network status and stuff that likely if we do something, we should wire those up to give the apps a sort of standard way to know, am I online or not, that kind of thing. And so the goal would, like I said, would be to allow the Flutter and HTML5 demos to build a native settings app for their, toolkit. Then, of course, Cooksa.val itself isn't standing still. Upstream has shifted focus to a new implementation in Rust as opposed to the original C++ one. That's referred to as a data broker, which Sven mentioned in his presentation yesterday. One thing to note is it doesn't actually implement the WebSocket API. So basically, it only has a gRPC API. That API, like I sort of mentioned with Cooksa.val, the C++ version, is very similar to BIS v1. So that's good for us because it means that logic-wise, the apps don't really have to change. It's just the call they make changes, basically. It is likely, based on what I've been told, that the C++ implementation will get deprecated this year. So we'll be highly motivated to switch to the Rust version at that point. This will likely happen, at least at some level, even if it's not an officially sanctioned task, because in order for us to keep using Cooksa, we're likely going to have to migrate. So I'm going to start evaluating building the data broker as opposed to the original server. And there's actually, the world is changing, so it's actually maybe a good time to start looking at building a Rust application using upstream Yocto and actually showing that in AGL. Because, Toyota have been pretty upfront that they're using Rust in-house, and it's happening. The world is going to move to these memory-safe languages, whether we like it or not. So we better start actually trying to show that we can support that. And like I said, the migration should be helped by the fact that the gRPC APIs are actually mostly the same between the server and the data broker implementations. So if I switch, or between myself and maybe some of the GSOC students, switch the our apps, our demo apps, to using the gRPC API, then the data broker probably becomes a lot more like just a drop-in that probably wouldn't require a lot of changes. Also in this space, there's a 4.0 version of the spec coming. 3.1 just got released, and as far as I know, 4.0 is probably 4 months away or something like that. But it already has some known impact. So one of the pull requests that's been discussed in the recent calls is they're actually going to change the naming in the schema and drop left and right as sort of indicators in the tree to use driver and passenger instead. So I actually jumped on the call last week and asked about this, and it actually is actually a thing that fits better with hardware. Basically, the ECUs all report driver side and passenger side as opposed to left and right. So it actually is viewed as being a change to make it quote unquote more in line with what actual vehicles do. So for us, it's mostly some search and replace and some of the apps like the HVAC. So we do have some flexibility here because Cooksa.val lets you pick what version of the schema to expose as a configuration option. But switching to the latest version when we do upgrade it seems pretty sensible because we're putting this in as a little bit of a technology demo. We want to show the latest version to AGL members, and so they can pick it up and look at using it, right? So we'll probably eat this in the fall probably when we do the next big upgrade. So that's it for the future development that I have planned. There's some other incidental things in this space around maybe some of the CAN configuration for the demos and stuff, but at a high level, those are the major things. So I gave a couple of presentations at a workshop in Japan in November, and the creating services one does talk a little bit more about the gRPC side than it does the VSS, but it does actually go into more detail about how the AGL service HVAC implementation is coded and shows a little bit more detail on what the signal responses look like and stuff like that. So if you want more low-level detail, then those are, it's a good presentation. And the using CAN services with AGL presentation talks about how the Cooksa DBC feeder is configured to actually push CAN data into the server. So if you actually want to add signals for your own demo, that's the presentation to look at. I actually have the DBC file and the YAML file that does the mapping and show how to configure putting a signal in and have it go up into Cooksa. So that's all my content. Does anyone have any questions? Yep.
I was only able to find something that I could use locally to build generate Rust from gRPC files or Konsulko.val. Did you?
Yeah, probably it would be the case that you generate it and check in the generated code. I'd have to go and actually look. Like in CMake, for most of the stuff I've coded up, I've used Mezen instead because it's more straightforward for gRPC, I've found. I'd have to go and see if there's actually a macro to make it go. This gentleman has his hand up, though.
Just basically to say that Tonic
Yeah.
has each main runtime, Frost, each main protobuf construction.
Yeah.
Frost can derive Rust code directly at build time from protobuf definitions.
Okay.
You don't need to check in with compile code. There's value in it because then you don't have to have protobuf C on your build systems, but you can reward it.
Yeah, it's one of those things that gets interesting around reproducible builds maybe a little bit because there's an argument either way that you can make, like whether it's better to actually always generate it or better to generate it once and check it in. But I mean, in theory, most of that stuff, it shouldn't change very much with respect to generated code unless you change the protobuf definition. But yeah, it's one of those things we'll have to investigate a little bit. I probably lean more towards the always generating it. I think I've wired that up in most of the stuff that I've built for AGL. And it is one of the things right now, there's an open bug in Jira where I've had discussion with Marius because he's written some gRPC APIs now for the compositor, is to have like a single repository where we put all the AGL API definitions in it. And then in our build process, that'll be the dependency of the apps and the server implementations so that we don't have to duplicate the protobuf definitions. Yeah. Yeah.
I'm relying on them to configure it properly locally, right?
Yeah, it is, well, there's a tension there, I agree. Because we would complicate the developer's life a little bit this way, because then if they did say, well, I want to add an API call, which is one of those things that you don't necessarily want arbitrary changes, right? So if we have this separate repo as opposed to having it in the server or the app repo, then there's like a two-step process, and the developer, we have to sort of document, well, if you're going to make this change, here's how you go about actually coordinating to make it the change in the template, like the API repository protobuf, and get it that your app sees it. So yeah, it's one of those things I have to work out. That's the reason why I didn't do it yet, is that I need to research a bit more, and yeah, it's easy to do Google searches and find big arguments on Hacker News about doing things different ways, or Stack Overflow, and finding out what someone calls a good workflow, how it actually works for us in practice is still, I think we'll have to experiment a bit. So it's a very good question, but it's something we'll have to hash out in the near future. For sure. Yeah. Yep.
If you're going to have a centralized API repository,
not yet. That's what we're. Yes, that's what I want to do.
would there be value in having a centralized definition of, for example, the set of signals that AGL applications consume?
Yeah. So that's one of those interesting things where. So VSS. That's the goal of the standard, right? That's and so it's one of those things I have yet to see somebody clearly say whether you would make a statement at a high level that if you're using VSS, you always have all of those signals. In my mind, that makes sense. Is anything you do, you would be an addition for your proprietary signals on top, but that the standard set in the schema should always be there for apps to use. And that if you do have extra stuff, you should start pushing that upstream to the specification, because that's the process, right? Like anybody can make a pull request on GitHub to try and get a signal added. And I know that at least from some of the discussions on the calls, you can fork the spec repo and modify the vspec files and generate your own custom VSS hierarchy. Hopefully people aren't doing that and cutting out most of the tree, because that would make it much more difficult to say that you could write an app and have it work anywheres. So I think that's a new thing that's going to be difficult to pin down for a while. So I think hopefully we'll see maybe somebody try to get an agreement that when people use Cooksa.val or some other implementation of a server for VSS, that if they say they are using VSS 3.1 or 4.5 or whatever, that it means that all of the signals in the upstream tagged version are there. Because I think it'll be very difficult to work with unless something like that kind of statement gets made. But right now, if you want a documentation for that specifically for AGL, I could set something up to try and generate it as our documentation improvement. I think right now I add 8 or 10 signals maybe on top, some of which I would like to get rid of. The steering wheel signals, some of it's to do with the cruise control, because I basically would need to write a little daemon to act as a sort of sensor-ish fusion type of thing, to take the signals and combine them to update the signals in VSS that exist, because the buttons do more than there's a behavior that is not actually mapping one-to-one to the signals in the VSS schema. They're around if you hit cancel when you're in cruise or blah blah, that's actually handling that, and I have to have some piece of logic somewhere to do that. Yeah, basically the Cooksa.val DBC feeder is very simple. I could probably tweak it a bit and add a little bit of logic there to say if this signal is true when this one is false, then update the VSS signal with this value. But right now it's too simple to support that kind of combinatorial logic. So it's one of those little things in the space where in a production vehicle, you probably have a daemon that's listening to a bunch of GPIOs or CAN signals, and you would internally have a bunch of logic to say, update the VSS signal to this value when this combination of states has happened. But yeah, we can definitely, we have a discussion about what all to document. That's probably very straightforward. Anybody else? Just on time somehow.
I just got a real
Yeah.
That's the purpose, by the way, that you talk about copy. I don't know if you're familiar with it. It's from BlackBerry.
Mm-hmm.
Originally just for QNX, but it's now been extended to Linux as well, I believe.
Okay.
And it's for creating insights from multiple CAN signals.
Oh, okay. Yeah. All right, well, we should talk about that a bit, because, at this point, like I said, we don't have pretty much direction on that front. The AGL members, like I said, all tend to have in-house stacks, right? So reusing an existing project is basically our goal now. We don't want to write our own CAN daemon, right? So if there's something else in this space we can pick up and do more complicated demos with to show using it, would be very interesting. So, yep, for sure. Anybody else? All right, well, thank you very much, and have a good afternoon.